All right. So first, where we are is particle kinematics. In a rotating coordinate system. And there are three results that we have. And everything is going to be based on these. And really, the second and third results are based on the first one. But the first one is the big result that says if you want to take a time derivative of any vector in a rotating coordinate system, the way to do that is calculate the vector's components dotted in that coordinate system as measured in that coordinate system. You know, this would be the end of it if it wasn't a rotating coordinate system. Those would be the same things. But with a rotating coordinate system, we also have to include the angular velocity of the coordinate system crossed with the original vector. Okay. Well, if you apply these to the position vector, you know, this works for any vector. If you do it specifically to the position vector, you get the velocity vector, which we can write two ways. The first one is the velocity vector is the dotted components of the position vector plus the angular velocity of the coordinate system crossed with the position vector. This can be, question? This can be written another way. Yeah. So this can be written another way also, just depending on how the information is given. So you can also write this as V is equal to the velocity vector as observed in the rotating coordinate system. You can think of this as, this is exactly the same thing. These are, it's sort of like synonyms for the same thing here. The derivatives of the components is the same thing as the observed velocity, plus omega cross P. And then the third result is for acceleration. So we can write the acceleration as, and this one gets messier because we have to apply this rotating coordinate system derivative now to this two-term thing from velocity to get the acceleration. And when you reorganize it and everything, you get px, py, pz all double dotted. Plus the angular velocity of the coordinate system dot. So that's the angular acceleration of the coordinate system, crossed with the position vector. Plus 2 times the angular velocity of the coordinate system crossed with the first time derivatives of the position vector components. Plus angular velocity of the coordinate system crossed with the quantity angular velocity of the coordinate system cross P. So you get this messy thing. That'll always be given on tests and stuff. So you don't have to memorize it, but if you do enough problems, you might by accident. And 2 of these 4 terms look a lot like the terms in the acceleration for a particle in circular or spherical motion. So be sure that you understand the differences, what the different variables mean and stuff. And we can also write this in the other way. We can write this as the acceleration is equal to what the rotating coordinate system thinks is the acceleration, the observed acceleration, plus omega dot cross p plus 2 times omega crossed with what the rotating coordinate system thinks is the velocity, plus omega cross p. Any questions about those? So when do you use the dot notation and when do you use the observed notation or way of thinking about it? Really, the only time you're going to use that component dot notation is when you're given the position as a function of time. Any other time, so let me write that down. So notice the component dot form is for when you're given the position vector as a function of time. So like, for example, if you're given that in a rotating coordinate system, P is equal to t squared cosine of t 5t. Then you'd use that component dot notation because it's easy to calculate those. In other cases, what we're going to have is circular motions. And with the circular motions, you'd use the observed way of thinking about it. We'll get to some examples like that later on. Okay, so the first rotating coordinate system that we're going to talk about is polar and cylindrical coordinates. So this is our first rotating coordinate system. So first of all, why would you ever use polar coordinates? So why do people ever use these? They can simplify math a lot. So there's simple math in polar and cylindrical coordinates for certain types of problems. So like, for example, if you have, that's just a guideline for me. And then let's see, so let's say we have a thing that's like, imagine this being way more symmetric than I'm making it look, but hopefully you sort of get the idea. Okay, so a shape like that. I mean, imagine trying to represent that function using parameterization or whatever. It would be kind of chaos, but in polar coordinates, this is nice and simple. You have a function that just says r is equal to 5 plus cosine of 8 theta. That's just such simple math for such a crazy looking thing. Or an ellipse. Let's say that we have an ellipse like that. This is represented as r is equal to 0.8, well, with the radius and stuff that I chose, the foci that I chose, over 1 minus 0.8 times cosine of theta. Okay, so in some cases it simplifies the math a lot. The problem, if you're doing dynamics with these shapes, so say that you want to do dynamics for a particle that's following one of these shapes, so imagine imagine the polar coordinates. So think of it as like r theta. You're used to thinking of the coordinates of a particle's position as being its position vector, but this is not a vector. So this is not a position vector. A position vector requires a component along one axis and then a component along a perpendicular axis, and that's not what this is. Okay, so these are not position components along perpendicular axes. So if you want to do dynamics, you have to define a coordinate system. And so the ones we're going to use are, so we're going to have this kind of underlying XY coordinate system that we're sort of referencing everything to. This one we're always assuming is not rotating. And as this particle moves around, so here's our particle. This is the position vector. But what's our coordinate system, in order to define the components of that position vector, we need a coordinate system. Well, the coordinate system we're going to choose is we're going to call, this axis centered at our reference origin. We're going to call this the ER axis. And then perpendicular to that, we're going to call this the E theta axis. And our position vector then in this coordinate system is equal to R times ER. And in our square bracket way of writing vector components, you can think of this as R0, 0, where this would be like this first one, I guess, would be our ER component. This would be our E theta component. And this would be our EZ component that we don't care about unless we're in cylindrical. I'm only putting that in for the cross products that we're going to have to do. And then, well, polar coordinates have an r and a theta, right? With this way of defining the coordinate system, theta didn't come up anywhere. So where does theta come into this? Well, theta is this guy, like going from our reference axis to here is theta. Okay, so the position vector is always just r, 0, 0. But theta is kind of this underlying rotation between our reference fixed coordinate system and our rotating coordinate system. And notice that this is a rotating coordinate system because as this particle moves around, you know, that theta is changing. Okay, do any of you remember from, I remember this when I took calculus, we were given expressions for the velocity and acceleration of a particle in polar and cylindrical coordinates. And it's kind of surprisingly messy, and there was no derivation or anything. But tell me if you've seen this before. So have you seen this in calculus? That the velocity in a rotating coordinate system is equal to r dot, r theta dot 0, or another way of writing that would be r dot times that ER axis plus r theta dot times that E theta axis. Does that look familiar to anyone? No? That might have been a thing that we used to get in the 1900s. Those were good times. And then they also, just gave us this, didn't derive it, but the acceleration vector was equal to, and this one is crazier looking. The first component is r double dot minus r theta dot squared. The second component is r theta double dot plus 2 r dot theta dot, and then 0 for z. And you can write this as the quantity r double dot minus r theta dot squared in the ER direction plus the quantity r theta double dot plus 2 r dot theta dot E theta. And they gave us that and made us do calculations, and it's pretty easy to do the calculations, but it's harder to understand what's going on, And so what we're going to do is we're going to derive these two expressions. So, come on. So I'm going to just set this aside, and we're going to derive these two things. And I think it'll help us sort of make sense out of what all the things in these equations are. Okay. Okay, so we're going to derive these using our expressions, our equations for the velocity vector and the acceleration vector in rotating coordinate systems. Okay. So the first one we're going to do is the velocity. So we know that the velocity is equal to the components dotted. So I will write that as let's see. So we know that we can write this as the observed velocity no, sorry to mess up your notes. This is better. So this is equal to, let's call it the r component of the position, dotted, and then the theta component of the position, dotted, and then the z component of the position, dotted, plus omega cross the position vector. And we just want to figure out what these things are before we, and then we'll just fill them in, plug them into our calculator and do the calculation. So first of all, this first thing, the time derivatives of the components of the position vector, this is the position vector given here. So the r component of the position, dotted, is, anyone want to go out on a limb on what I'm going to call this? R dot, yep, exactly. So this is R dot. And then the other two are zeros. So if you take the time derivatives of those, you just get 0 and 0. And then we have the position vector. What about the angular velocity vector? Well, this is a planar motion, a planar rotation. And so our omega of this coordinate system is just the time derivative of that theta. Are you with me on that? Acting in the z direction, because that's how angular velocity directions work. I have it defined according to the right-hand rule as being in the direction of the positive z. So, so this is just equal to 0, 0, theta dot. And the position vector is what we had before, r0, 0. So now I can plug this stuff in and we get v is equal to r0, 0. Nope, I did the wrong one. R dot 0, 0 plus 0, 0 theta dot crossed with r0, 0. I just plug the stuff in and we get r dot, and then this cross product, you get a double negative of r times theta dot, so r theta dot 0. So it matches what we were given above. Now that would be cool if you'd ever seen that before, but apparently you haven't. But it's cool to me because I had seen it before. And now we're going to do the same thing for the acceleration. We just have more terms to worry about. So the acceleration of a particle in polar coordinates is the time derivatives, the second time derivatives of the position components plus omega dot crossed with the position vector. So that's PR, P theta, Z. plus 2 times omega crossed with the first time derivatives of the position components. So that's PR dot, P theta dot, Z dot. And then plus capital omega cross quantity, capital omega cross P. Yes?
So for that first part of the acceleration equation, I think that at the first big result,
Yeah.
that angular velocity or acceleration times PR p theta pz, is that from like taking the derivative of velocity, should that be PR dot p theta dot z dot, or where is that?
Which term again?
It's being crossed with the omega dot.
Okay, yeah. With the omega dot. Okay, yep.
Where did that vector come from?
Okay, yeah. That comes from, we did this yesterday, and that's, so that's the second term of this expression for the acceleration. It's just that now our position vector components are an R component, a theta component, and a Z component. Okay, and now we want to calculate these. I think this is always a good way to go. Like once you write down this equation, just go through and get all the individual vectors that you need, and then you can just plug them in. You need some sort of bookkeeping strategy because it's messy, you know. But so PR double dot, P theta double dot, Z double dot. Our PR is R, and so double dot is just R double dot. Our P theta is 0, so second time derivative of 0 is 0. Our Z is 0, so again, 0. What about our capital omega dot? Well, our capital omega was 0, 0 theta dot. And so our capital omega dot is 0, 0 theta double dot. Our omega, just like before, is 0, 0 theta dot. Our first time derivatives of the position are R dot 0, 0, just like it was for the velocity calculation. And our position vector, just like it was for the velocity calculation, is R 0, 0. And now we're just plugging all that stuff in. So the acceleration vector is equal to R double dot 0, 0 plus 0, 0 theta double dot crossed with the position vector plus 2 times capital omega 0, 0 theta dot crossed with the components dotted. So that's R dot 0, 0. Plus 0, 0 theta dot crossed with the quantity 0, 0 theta dot crossed with our position R00. Okay, so we'll do this piece by piece. So these two cross together are a double negative R theta dot in the y component. So this is 0 R theta dot 0. And then we'll cross this one with this one. And so we get in the x direction negative R theta dot squared, then 0, 0. Any questions about that one? Yep.
So like in the Watermill equation, we were able to like piece up the sections into like what they interpret what they mean.
Yeah.
Can we do the same for this equation?
It's a little messier, but you can see that this last term, the one we just did, is like an unobserved centripetal acceleration that we were not able to see because our coordinate system is rotating. Okay. This one is, well, I don't really have an answer for you on this one, but it happens to have a name. This is the Coriolis term of the acceleration. It has to do with, you could actually find YouTube videos that would try to explain that to you. I don't think I'm going to try to say anything about it. This one is, you can think of that as like an unobserved tangential acceleration that you don't see because the coordinate system is rotating. And then this one is the part that that the coordinate system observes. So if, like, one way to think of it is, if the coordinate system is not rotating, all you have is that first term. That is the definition of the acceleration in a non-rotating coordinate system. The three additional terms are like corrections that come from the coordinate system rotating. Okay, so the Coriolis acceleration. And I don't know the history of like why that was named or whatever, but I mean, my best guess is that before this was all done as vector calculations, this was related to somebody trying to make sense out of this, and you know, they thought of that as sort of a quantifiable thing that they could measure. But it's funny that one term has a name and nothing else does. And that's a key character in the Simpsons episode where Bart goes to Australia to apologize to the Prime Minister. So if you want to understand this, you should YouTube that episode. Okay, so this, we have a double negative in the y direction, and then don't forget to multiply by the 2. So we have 0, 2 r dot theta dot 0. And then this one, we have a double negative, and we, in the y direction, we have r theta double dot 0. And so putting this all together, we get an acceleration vector of, so add up the two first components, the two r components, and you get r double dot minus r theta dot squared. Add up the two second components, and you get r theta double dot plus 2 r dot theta dot 0. And I think that matches what I gave you. Yep. And then what if this is cylindrical coordinates instead of polar coordinates? Well, the only thing that's different is you also have a z component. So in cylindrical coordinates, so you just put on the z dot and the z double dot. So the velocity in cylindrical is whatever we had below, r dot, r theta dot, and then z dot. And acceleration is equal to r double dot minus r theta dot squared. Then the second component is r theta double dot plus 2 r dot theta dot, and then z double dot for the z component. I mean, really, you can think of polar as polar is cylindrical. And I mean, notice that if you use these equations for a polar calculation, your z dot would just be 0, your z double dot would be 0. So in a way, you can just think of everything as both of those as cylindrical. You've also probably occasionally, once or twice, done stuff in spherical coordinates. I'm not going to derive that, but you can do that derivation the same way. It just takes more sort of precise thinking about different axes and stuff. I'm not gonna do that, but anybody have any questions about this? So the first homework problem that you're gonna do is gonna be just a case where I give you some polar values and ask you to apply this basically. Okay. So basically just trying to treat you like your calculus students in the late 1980s. Okay, but now we're getting to the really cool stuff. The thing that you're going to do the most problems related to with rotating coordinate systems, and this is superimposed motions.
Professor?
Yeah.
What's the whiz today? Like, we haven't really added on that much.
Yeah.
From the last.
You're right. I definitely noticed that.
Will we have this on?
Nope, it's not on there. It's just, I mean, remember they're all cumulative, so I mean, I can just use all the old stuff again when I write this quiz. I already have it written. Okay, so superimposed motions. And so here is the example we're going to do. I'm going to imagine a like a little bar coming out of the wall. And a thing on here that can spin around the axis. That is called an armature. And I'll try to draw it nicely. And so what we're talking about, bless you, is this armature is rotating around like this. And then at the same time, this wheel is rotating around like this. Let's say that that's 5 radians per second. And we want to calculate the acceleration of this point P. Okay. We might want to calculate the velocity too. Acceleration is more useful to us because we can use it in Newton's laws. Yep.
Is that whole bar just fixed?
It's the bar is fixed and just the added on thing spins. So we want to calculate the acceleration of that point P. And before we go into doing this, so first, compare to this thing where we have a hinge on the wall that's connected to one body, and then a hinge connects it to another body. And we're given that this has an angular velocity like that, and this has an angular velocity like that, and we want to calculate the acceleration of this P. So what's the fundamental difference between these two cases?
Between linear axis, the one is
Yeah.
Three-dimensional also?
Okay, so yeah, you're right on it, but let's think about, let's just think about like sort of a like precise language for this. These two. Okay, so this, the one on the bottom, we've already done a bunch of times and gotten tired of it and set it aside, as a plaything for children, This, but no, this thing, this one is what we're on now, and it's going to take some thinking. So what's the difference? I mean, they look different, but the fundamental difference here is notice that so notice that in both of these two cases, first of all, there's a horse and a cowboy. So think about it that way first. One of these bodies is riding the other one, and there's no way around that fact. Okay. This body is riding this body, and it's not the other way around. Okay. And this body, the wheel is riding this armature, and there's no other way around. Okay. But the difference is, as the horse moves in this one, the axis of rotation of the cowboy stays constant. Okay, so as this thing moves, the axis of rotation is still in the z direction. Okay, but look at what happens with this one. As the horse, the armature moves, every time it moves a couple degrees or whatever, anytime it moves any angle at all, it changes the axis of rotation of the cowboy. Okay. So this one we can do with our old approaches. This one, what we're going to do is fix a coordinate system to the horse. The benefit of that is that if you fix a coordinate system to that armature, then according to that coordinate system, the motion of this wheel is just a simple circular motion. And then we can use a rotating coordinate system approach. Yep.
So the cowboy in this case is mounted at an angle.
It's what?
Is it mounted at an angle?
It's not supposed to be.
Okay.
Yeah, it's not supposed to be. It's sort of, my perspective looks a little wonky there.
Okay.
Okay, so the fundamental difference here is that in the second, okay, so first I said the thing about the horse and the cowboy. So there's always a horse and a cowboy. Oh, what could mess this up is that song, Save a Horse, Ride a Cowboy. Don't listen to that song during this class. That'll confuse you. In this class, cowboys always ride horses. Okay, so there's always a horse and a cowboy. In the second example, motion of the horse doesn't affect the axis of rotation of the cowboy. In the first example, and so, in this case, so we don't need to use a rotating coordinate system approach. In the first example, the motion of the horse changes the axis of rotation of the cowboy. And so in this case, we're going to use a rotating coordinate system approach. And we're going to fix our coordinate system to the horse. And if you do that stuff, you'll always get these problems right. Okay? So let's just go through this example. So I'll draw it again and try to get the perspective right. I know I have art students in this class, for one. I don't want to get called before the art department ethics board. I think that was my problem. I made the wheel look too fat. That's my working hypothesis. Yeah, doesn't that look better this time?
I think it looks about the same.
I don't think so. We'll have to agree to disagree on that. Okay, so this one I think was going this direction at 20 radians per second. And this one is going this direction at 5 radians per second. But notice that that second one, the green value, that's like that is a rotation that only makes sense relative to the red one, Otherwise, it's a lot more complicated what's going on. And then our coordinate system. So let's fix our coordinate system. Let's put it right here at the center of the disk. And it doesn't matter what directions we choose for the axes. I'll go X this way, Y this way, and Z this way. Yep.
So for this problem, is that first body almost just like a bearing or a sleeve on a shaft?
Yeah, exactly. It's a sleeve. Yep.
Is that second body attached to the shaft or the first body?
The wheel.
Yeah.
The wheel is attached to the shaft that's rotating. So this thing is doing this is doing like a compound motion.
Oh, so it's like you have two circular motions. So it's
Yes.
the edge of the circular motion.
Exactly. Yes. Yes.
Nice. Okay.
Two like superimposed circular motions. So this will rotate, like when this rotates 90 degrees, now the disc will look like a blade does, and that point P will be like in the back. I didn't draw the point P. But this thing is this thing is spinning while this thing spins.
Oh, okay.
And this is the point P that we want to calculate the acceleration for. Okay, so I put my coordinate system on the horse. I already drew that in black. And we know that the acceleration of this point P is equal to the observed acceleration according to that coordinate system plus omega dot crossed with the position vector plus 2 times omega crossed with the observed velocity vector plus omega cross quantity omega cross P. And now our job is just to come up with all these these variables. Okay. Well, our coordinate system is rotating with that sleeve, with that armature. So our omega, that's the angular velocity of the coordinate system, is 20 about the positive x-axis. So this is 20, 0, 0. Any questions about that?
Yeah, you can do this positive 20.
Right-hand rule. So your fingers are rotating along with the coordinate system's doing what the red thing is doing. So your fingers are curling with the red rotation, and that puts your thumb in the positive x direction.
Okay.
And then what about the angular acceleration of our coordinate system? Well, these are given as constant. If they weren't constant, we'd be told what those angular accelerations are. So this is 0. Our position vector. So the position vector goes from the origin of the coordinate system to the point we care about. The origin is at the axis of that disk. Oh, I didn't give a radius. Let's pretend I did, though. Let's say that earlier I told you that the radius was 0.1 meters.
The radius of the first.
The disk. Yeah.
Are we doing this one in polar coordinates?
Nope. This is just regular x, y, z. And so the position vector here from the origin to P is just 0, -1, 0. What the? Where did that come from? What class is this? Okay, why does it say 227? Okay, so 0, -0.1, 0. That's the position. Now we have to think about the observed velocity and the observed acceleration. Well, what kind of motion is P in to an observer that's fixed, that's rotating with that armature, that's fixed to that armature? Circular. That's all it is. That P is just in circular motion as far as that coordinate system knows. Okay, and that's how this is always going to work on these problems. Yes?
Where's the observer fit?
The observer is, so that coordinate system is fixed to this sleeve. So when this sleeve is rotated another 90 degrees, X will be pointed that way. Y will be pointed straight out towards us. And Z will be pointed straight down. Okay. Are you with me on that? All right, so according to this coordinate system, so the velocity vector that's observed, this is circular motion. So we're just going to calculate this as omega of, so now this is little omega because we're talking about the motion of the disk. Okay, so this is just omega crossed with the r vector. And we have to think about the definition of the r vector. In this case, the way it's set up, the r vector and the p vector are going to be the same. Sometimes that's going to be the case, but it's not always the case. Okay, so each time think carefully about that definition. So what's the angular velocity of the body, the disk, according to that coordinate system? So think of the right hand rule. It's going, your hand is curling this way, so your thumb is in the negative z direction. So it's going to be 0, 0, negative 5. So omega is 0, 0, negative 5. And now the r vector, that's a vector that goes from what to what? Exactly. So that's the same as the p vector in this case, but don't get lulled into a false sense of security on that, okay? So r, that's just because in this case we happen to put the origin at the center of this circular motion, okay? So r is equal to 0, negative 0.10. And so the observed acceleration is 0, 0, negative 5 crossed with 0, negative 0.10. And so you get, in the x direction, negative 0.500. That's the observed velocity according to that coordinate system. If all you know is what that coordinate system sees, imagine it being a video camera or something. If all you know is the data from that video camera, then this is your best guess at what the velocity is.
Why do for the big omega we use the velocity of the twin for the observed is 5.
Right. So the big omega is always going to be the angular velocity of the horse.
Okay.
And the small omega is always going to be the angular velocity of the cowboy. Because we're always fixing the coordinate system to the horse. It's always moving with the horse. If you really had a video camera attached to a horse, you know, and you are using that video camera to measure accelerations, it would look like the cowboy was insane, you know? Like you'd be looking at this picture, it would look like the horse was still and the cowboy would just be bouncing all over the place, screaming for his mom or whatever, you know? So that's what we're talking about here. We're removing the motion of the horse from the equation temporarily and only considering what that video camera sees.
That's what the observed.
Yes, that's right. So, and now we have to do the same thing for the acceleration, and we're going to have to use the watermelon equation. So the observed acceleration is all ripe watermelons will rot. This goes away because our alpha is 0. So alpha is 0. R is the same thing as it was before, 0, negative 0.10. Omega, This is the omega of not the coordinate system, but the body. This is the angular velocity of the cowboy. So this is, what was it, -5, 0, 0, -5. And so now we can plug this in. And we get 0, 0, -5 crossed with the quantity 0, 0, -5 cross, and R is 0, -0.10. So if you cross these, you get -0.500. And now cross these, and you get double negative, so 0, positive 2.50. And now finally we can put all this together. The acceleration of P is equal to the observed acceleration plus omega dot cross P, that's 0 because omega dot is 0, plus 2 times capital omega 20, 0, 0, crossed with the observed velocity, -0.500, plus capital omega, so 20, 0, 0, cross quantity 20, 0, 0, crossed with the position vector 0, -0.10. So if you cross these, you get 0, 0, 2, -2. And if you cross these, you get a double negative and then 0, 40, 0. And then this one, cross product of two parallel things is 0, so this goes away. No Coriolis part of this acceleration. And so altogether, the acceleration of that P is equal to 0, 42.50. And then this is an acceleration that you can use in Newton's laws. If you had used that observed acceleration in Newton's laws, you would have gotten the wrong answer. But this one will work. So this is the acceleration that will work in Newton's second law, I guess, specifically. Any, what? Now. Yes.
So to sum this up, if you have two things that are spinning, you can just put a coordinate system on one. Yes.
That's right. If so,
That's pretty general across the board.
yeah, so you always put the coordinate system on the one that is like the base of the other one. Yep, that's right. And you don't have to do it unless that base, that horse, its motion is affecting the axis of rotation of the cowboy. Yep.
And so when assigning that spot for the coordinate system, is it always where the two bodies connect?
You can put it wherever you want, and we'll do some examples like that coming up. We can do this problem again and put the origin of the coordinate system back at the wall. It'll change some values that we put into this equation, but in the end, the answer will be the same. It's just going to take some time for sure and some practice for everyone to get used to this. And that's what we're going to do for the next few classes is just examples. But yeah, another question?
Would we be, we need to be given more information than like do it at the wall?
I guess we'd have to know the length of that. Yeah,
Okay.
that's right.
And if that first body was stationary, would this just be as a simple circumference?
Exactly. Exactly. Okay, let's do the quiz.